Welcome back to the channel. As we move forward with Model 4, in this session, we'll take an in-depth look at unsupervised machine learning, where we delve into powerful techniques like clustering and dimensionality reduction to unlock insights from unlabeled, high-dimensional data. In today's data-driven world, machine learning engineers and data scientists often face the challenge of analyzing complex datasets with numerous features. This presentation explores how clustering algorithms uncover hidden patterns without explicit labels, and how dimensionality reduction techniques, such as principal component analysis and singular value decomposition, simplify these datasets while preserving their core structure. We'll demonstrate how these unsupervised learning methods enhance model performance and reduce computational complexity through real-world applications ranging from image processing to recommendation systems. By the end, you'll gain a solid foundation in both clustering and dimensionality reduction, empowering you to efficiently tackle a wide range of data science and machine learning challenges. What is unsupervised learning? Definition: a type of machine learning where algorithms find patterns in unlabeled data without explicit instructions on what to look for. The system must discover structure through self-organization of the data. Key characteristics: works with unlabeled data, focuses on finding hidden patterns, requires minimal human supervision, and emphasizes data exploration rather than prediction based on known outcomes. Common applications: customer segmentation for targeted marketing, anomaly detection in cybersecurity, market basket analysis for retail, dimensionality reduction, and feature extraction from complex datasets. Unlike supervised learning, which requires labeled examples to train on, unsupervised learning algorithms must discover the inherent structure within data. This makes them particularly valuable when working with large, unlabeled datasets where manual annotation would be impractical or impossible. Clustering, the foundation of unsupervised learning. Clustering algorithms. K-means, hierarchical, density-based spatial clustering of applications with noise, and more. Similarity measures. Euclidean, Manhattan, cosine distances. Goal of clustering: group similar objects together while separating dissimilar ones. Clustering forms the backbone of unsupervised learning by organizing data points into meaningful groups based on their inherent similarities. The effectiveness of clustering depends on choosing appropriate similarity measures that capture the relevant relationships in your data. Different algorithms make different assumptions about what constitutes a cluster, leading to varied results on the same dataset. Understanding these differences is crucial for selecting the right approach for your specific problem. K-means clustering, simplicity and efficiency. Choose K clusters. Select the number of clusters to partition the data into. Initialize centroids. Randomly place K centroids in the data space. Assign points. Group each data point with the nearest centroid. Update centroids. Recalculate centroids as the mean of all points in each cluster. Iterate until convergence. Repeat assignment and update steps until minimal changes occur. K-means is one of the most popular clustering algorithms due to its simplicity and computational efficiency. It excels at finding spherical clusters of similar sizes and works well when the number of clusters is known or can be estimated reasonably. K-means in action, customer segmentation. In retail, K-means clustering helps identify distinct customer segments based on purchasing behavior. By analyzing metrics like purchase frequency, average spend, and product categories, retailers can discover natural groupings among their customers. For example, the clustering might reveal segments such as frequent small spenders, occasional big spenders, and loyal mid-range customers. These insights enable personalized marketing strategies, targeted promotions, and improved customer experience tailored to each segment's preferences. Hierarchical clustering, building a tree of relationships. Agglomerative, bottom-up. Starts with each data point as a separate cluster and progressively merges the closest pairs until all points belong to one cluster. Steps: start with n clusters, one per data point. Merge the two closest clusters. Update distances between the new cluster and others. Repeat until only one cluster remains. Divisive, top-down. Begins with all data points in a single cluster and recursively splits into smaller clusters. Steps: Start with one cluster containing all points. Split the cluster into two dissimilar groups. Select a cluster to split further. Repeat until each point is its own cluster. Hierarchical clustering creates a multi-level tree structure, called a dendrogram, that shows relationships at different scales. This approach is particularly valuable when the data has an inherent hierarchical structure or when you want to explore clustering at multiple levels of granularity. Dendrogram interpretation, reading the tree. Examine the tree structure. The dendrogram represents the entire clustering process. The y-axis shows the distance or dissimilarity at which clusters are merged. Identify natural clusters. Look for long vertical branches, which indicate significant distances between merged clusters. These represent natural separation points. Cut the tree. Draw a horizontal line through the dendrogram to create clusters. Points connected below the line belong to the same cluster. Validate results. Examine the resulting clusters for meaningful patterns and adjust the cut height to find the optimal number of clusters. Dendrograms provide a visual representation of the hierarchical clustering process, making it easier to determine the appropriate number of clusters and understand relationships between data points. The height at which branches merge indicates the dissimilarity between clusters. DBSCAN, density-based spatial clustering. Density-based approach. Clusters are defined as dense regions separated by sparser areas, allowing for the discovery of arbitrarily shaped clusters rather than just spherical ones. Key parameters. Epsilon, maximum distance between 2 points to be considered neighbors. Min points, minimum number of points required to form a dense region. Advantages. No need to specify the number of clusters beforehand, effectively handles noise and outliers, discovers clusters of arbitrary shapes and sizes. Limitations. Struggles with varying densities across the dataset, sensitive to parameter settings, computationally more expensive than k-means for large datasets. DBSCAN excels in scenarios where clusters have irregular shapes or when noise identification is crucial. Unlike k-means, it doesn't assume that clusters are convex or of similar sizes, making it more flexible for complex data distributions. DBSCAN application, geographic clustering. Crime hotspot detection. DBSCAN can identify areas with high crime density while filtering out isolated incidents. Law enforcement agencies use these insights for resource allocation and preventive policing strategies. Customer distribution analysis. Retailers analyze customer address data to identify natural geographic clusters, helping determine optimal locations for new stores or targeted marketing campaigns. Epidemic monitoring. Public health officials use DBSCAN to track disease outbreaks by identifying unusual clusters of cases, enabling rapid response and containment measures. Geographic clustering with DBSCAN offers valuable insights across various domains by identifying natural spatial patterns. The algorithm's ability to handle noise and discover irregularly shaped clusters makes it particularly suited for spatial data analysis. Evaluating clustering performance. Internal validation. Measures based solely on the dataset and clustering result without external information. External validation. Compares clustering results with known class labels, when available. Relative validation. Compares different clustering algorithms or parameter settings. Visual assessment. Human evaluation of clustering results through visualizations. Evaluating clustering performance is challenging since unsupervised learning lacks ground truth labels. Internal validation measures assess properties like cohesion, how close objects within a cluster are, and separation, how distinct clusters are from each other. When some labeled data is available, external validation metrics can provide additional insights. In practice, a combination of quantitative metrics and qualitative assessment often yields the most reliable evaluation. Silhouette score, measuring cluster quality. Calculate A of I. Average distance between point I and all other points in its cluster. Calculate B of I. Average distance between point I and all points in the nearest cluster. Compute silhouette S of I. S of I equals B of I minus A of I, divided by the maximum of A of I and B of I. Average all silhouettes. Overall score is the mean of all individual silhouette values. The silhouette score measures how similar an object is to its own cluster compared to other clusters. Values range from -1 to 1, where higher scores indicate better defined clusters. A silhouette score near 1 means data points are well matched to their clusters and poorly matched to neighboring clusters. This metric helps evaluate the optimal number of clusters by comparing silhouette scores across different clustering configurations. It's particularly useful for algorithms like k-means where the number of clusters must be specified in advance. Other clustering evaluation metrics. Davies-Bouldin Index. Description. Average similarity between clusters, where similarity is the ratio of within cluster distances to between cluster distances. Range. Greater than or equal to 0. Ideal value. Lower is better. Kolinsky-Harabas Index. Description. Ratio of between cluster variance to within cluster variance. Range. Greater than or equal to 0. Ideal value. Higher is better. Dunn Index. Description. Ratio of the minimum intercluster distance to the maximum intracluster distance. Range. Greater than or equal to 0. Ideal value. Higher is better. Adjusted Rand Index. Description. Measures the similarity between two data clusterings, adjusted for chance. Range. -1 to 1. Ideal value. Closer to 1. Beyond the silhouette score, several other metrics help evaluate clustering quality from different perspectives. The Davies-Bouldin and Kolinsky-Harabas indices focus on cluster separation and compactness, while the adjusted Rand index is useful when ground truth labels are available for comparison. When selecting evaluation metrics, consider your specific goals and data characteristics. Using multiple complementary metrics often provides a more comprehensive assessment of clustering performance. The elbow method, finding optimal K. The elbow method helps determine the optimal number of clusters for k-means by plotting the within cluster sum of squares against different values of k. As k increases, WCSS always decreases, but the rate of decrease changes significantly at the elbow point. This point represents the value of k where adding more clusters provides diminishing returns. In our example, the elbow occurs around k equals 4, suggesting this is a reasonable number of clusters for this dataset. While useful, the elbow method should be combined with domain knowledge and other evaluation metrics for robust cluster selection. Real-world applications of clustering. Retail. Customer segmentation for personalized marketing, inventory management based on purchasing patterns, store layout optimization through basket analysis. Healthcare. Patient stratification for personalized treatment plans, disease subtype discovery, anomaly detection in medical imaging, gene expression analysis. Finance. Fraud detection through unusual transaction patterns, investment portfolio optimization, credit risk assessment, customer profiling for targeted services. Content organization. Document clustering for information retrieval, recommendation systems based on user behavior, image organization, news aggregation. Clustering algorithms have transformed how organizations derive insights from their data across numerous industries. By identifying natural groups within complex datasets, these techniques enable more personalized services, efficient operations, and innovative product offerings. The flexibility of clustering approaches means they can be applied to virtually any domain where pattern discovery and unlabeled data is valuable, from social network analysis to urban planning and scientific research. Key takeaways: clustering techniques. 3 core algorithms. K-means for spherical clusters, hierarchical for nested structures, DBSCAN for irregular shapes and noise handling. 4+ evaluation metrics. Silhouette score, Davies-Bouldin index, Kolinsky-Harabas index, and visual assessment techniques. Infinite applications. Virtually unlimited use cases across industries, from customer segmentation to anomaly detection and scientific discovery. Unsupervised learning, particularly clustering techniques, provides powerful tools for uncovering hidden patterns in unlabeled data. By mastering these algorithms and their evaluation metrics, you can extract valuable insights that would otherwise remain hidden in complex datasets. As you apply these techniques to your own projects, remember that the best approach often combines multiple algorithms and evaluation methods, guided by domain knowledge and clear business objectives. The field continues to evolve with new algorithms and applications, making it an exciting area for ongoing exploration and innovation. Dimensionality reduction techniques in unsupervised learning. In today's data-rich environment, machine learning engineers and data scientists frequently encounter datasets with numerous features. While these high-dimensional datasets contain valuable information, they also present significant computational and analytical challenges. What is dimensionality reduction? Simplifies models. Reduces model complexity, helping prevent overfitting and improving generalization. Reduces computation time. Decreases training time and resource requirements for machine learning algorithms. Removes noise. Filters out irrelevant variations in data, focusing on meaningful patterns. Improves visualization. Enables effective visualization of high-dimensional data in 2D or 3D space. Dimensionality reduction transforms your dataset by projecting it into a lower dimensional space while retaining its key characteristics. This process is essential for pre-processing and unsupervised learning tasks like clustering and anomaly detection, where patterns must be identified without labeled examples. The curse of dimensionality. Computational complexity. Exponential increase in computational resources needed. Visualization challenges. Impossible to directly visualize beyond 3 dimensions. Increased sparsity. Data points become sparse and distances less meaningful. As dimensions increase, the volume of the space increases so quickly that available data becomes sparse. This phenomenon, known as the curse of dimensionality, makes finding patterns increasingly difficult. For example, in a 10,000 dimensional space, even millions of data points become effectively isolated. Dimensionality reduction addresses this challenge by transforming features into a lower dimensional space that preserves the essential structure of your data. This transformation makes pattern recognition more computationally feasible and statistically reliable. Principal component analysis. Standardize data. Normalize features to have zero mean and unit variance. Compute covariance matrix. Calculate how features vary with respect to each other. Calculate eigenvalues and eigenvectors. Find directions of maximum variance in the data. Project data. Transform original data onto new principal component axes. PCA transforms your data into a new coordinate system where the first principal component captures the highest variance in the data. Each subsequent component is orthogonal to the previous ones and captures decreasing amounts of variance. This technique is particularly valuable when you need to reduce dimensions while preserving as much variability as possible. For example, in customer segmentation, PCA can reduce hundreds of customer attributes to a few key dimensions that capture essential buying patterns. PCA in facial recognition. Eigenfaces. PCA identifies base components, eigenfaces, that represent facial features across a dataset. These eigenfaces capture the most significant variations in facial structure. Dimension reduction. A 100 by 100 pixel face image with 10,000 dimensions can be represented using just 50 to 100 eigenface components, dramatically reducing computational requirements. Recognition process. New faces are projected onto the eigenface space and compared against known faces using their reduced dimensional representations, enabling efficient identification. Facial recognition exemplifies PCA's power in real-world applications. By decomposing face images into eigenfaces, we transform a high-dimensional pixel space into a compact representation that captures essential facial characteristics while discarding noise and redundant information. Singular value decomposition. Matrix decomposition. Decompose matrix A into U, sigma, and V transpose. Dimensionality reduction. Keep only largest singular values. Data reconstruction. Approximate original matrix with reduced components. SVD decomposes a matrix A into three matrices, U, which contains the left singular vectors, sigma, which holds the singular values, and V transpose, which contains the right singular vectors. By keeping only the largest singular values and their corresponding vectors, we achieve dimensionality reduction while minimizing information loss. This technique is compelling for recommendation systems, where user-item interaction matrices are typically large and sparse. Netflix's recommendation algorithm famously utilizes SVD to decompose user movie rating matrices into latent factors that represent user preferences and movie characteristics. PCA versus SVD, when to use each. Characteristic. Data centering. Requires centered data. Works with raw data. Matrix requirements. Works with square matrices. Works with any matrix. Computational efficiency. More efficient for smaller datasets. More efficient for sparse matrices. Primary applications. Feature extraction, visualization. Recommender systems, text mining. While PCA and SVD are mathematically related, PCA can be implemented using SVD. They serve different use cases in practice. PCA focuses specifically on finding directions of maximum variance in centered data, making it ideal for exploratory data analysis and visualization tasks. SVD offers greater flexibility as it works with any matrix without requiring centering. It excels in applications like collaborative filtering for recommendation systems and latent semantic analysis for text mining, where uncovering latent factors in the data is the primary goal. Dimensionality reduction, practical applications. Image processing. Efficient compression and facial recognition. Text mining. Topic modeling and document classification. Recommender systems. User preference modeling in e-commerce. Bioinformatics. Gene expression analysis and protein structure prediction. Dimensionality reduction techniques have become essential tools across numerous domains. In genomics, researchers use these methods to analyze high-dimensional gene expression data with thousands of genes but relatively few samples. Financial analysts employ them to identify patterns in market data with hundreds of indicators. As data continues to grow in volume and complexity, mastering dimensionality reduction becomes increasingly valuable. By thoughtfully applying these techniques, data scientists can extract meaningful insights from seemingly overwhelming datasets, enabling more effective pattern recognition and predictive modeling. Summary: Dimensionality reduction and PCA. High-dimensional data challenges. Modern datasets with many features cause higher complexity and analysis issues due to the curse of dimensionality. Purpose of dimensionality reduction. These techniques reduce variables while preserving key information, making data easier to visualize and analyze. Core techniques, PCA and SVD. Principal component analysis identifies directions, also known as principal components, that capture the most variance in the data. Singular value decomposition is a matrix factorization method that breaks down data into simpler, interpretable components. Preserving essential patterns. These methods reduce dimensions but keep key patterns vital for analysis and model performance. Real-world applications. Dimensionality reduction is widely applied in fields such as image processing, for example, face recognition, noise reduction. Recommendation systems, for example, compressing user-item interaction matrices for collaborative filtering. Enhancing unsupervised learning. Simplifying data boosts the performance and clarity of unsupervised algorithms like clustering and anomaly detection. Strategic tools for data scientists. Dimensionality reduction is key to handling complex data and gaining valuable insights. Thank you and upcoming module, Deep Learning. We truly value your active participation in our machine learning journey. Next session, we'll dive into Module 5, Deep Learning. This module will provide a comprehensive exploration of neural networks, starting with the fundamental principles and structure of basic neural networks, and progressing to more sophisticated and advanced architectures. We will examine how these models function, their key components, and their practical applications in solving complex machine learning problems. Stay connected. Subscribe, like, and share to continue your learning adventure.